Just say one small thing, because in keeping with the fact that it's great that so many Indians have made these remarkable contributions, and we are now going to have a talk, let me just say, by Professor Bala Iyer on LIGO-India. But just before that, let me say that we were all really thrilled on the evening where the announcement was made that the Prime Minister of India, Shri Narendra Modi, put out 3 tweets about the LIGO discovery, and I'll read 2 of them out because they pertain to Indian contributions. His second tweet said, "Immensely proud that Indian scientists played an important role in this challenging quest." And then the third tweet said, "Hope to move forward to make even bigger contributions with an advanced gravitational wave detector in the country." So I think this is really great news. This news itself, I think, is because of the work done by a number of people, including, of course, Professor Bala Iyer, as we've heard, but also many others. And I'm very happy that Professor Tarun Souradeep is also here. He's the spokesperson for the LIGO-India collaboration. And so we really look forward to getting some more positive news. So with those words, I invite Professor Bala Iyer, who is now at the ICTS, to tell us about LIGO-India towards gravitational wave astronomy.
So before I start talking about LIGO-India, I think I would like to say that it's indeed great when you find your students more capable than yourself. And I'm sure that the last 2 talks you heard, you know that source modeling and data analysis in India is in very capable hands. So thank you, Ajith. Thank you, Arun. I really wish that if I knew Tarun was coming, I would have insisted that he gives this particular talk so that you are convinced that LIGO-India, if it happens, is also in very, very capable hands. The baton has really passed over, and therefore we should be very happy that the next generation is ready to take up the challenge which LIGO-India will actually pose. So with those remarks, let me go to my presentation. There is an International Gravitational Wave Committee, and in 2010 it came with the Future of Gravitational Wave Astronomy, a global plan. It basically tried to put out over the next 30 years what needs to happen. And the basic message was a truly global array of gravitational wave antennas separated by intercontinental distances is needed to pinpoint the sources in the sky and to extract all the information about the sources encoded in the gravitational wave signal. And therefore, the first priority is to expand the network, adding further detectors with appropriately chosen intercontinental baselines to really extract information from gravitational wave analysis. 2010, you had these detectors in Livingston and Hanford and the detector in Europe. And for what is important for LIGO-India, originally the plan was to put 2 interferometers in the same beam tube at Hanford and 1 at Livingston. So LIGO is 2 sites but 3 detectors. As you have heard, there has been a remarkable legacy of gravitational wave research starting from 1990, work by my distinguished colleague Sanjeev Durandar on data analysis, as Arun pointed out, and work in my group on source modeling. We also know that there was an attempt to start an experimental program around the same period, but it didn't get funded. But again, we are very, very fortunate that all the postdocs and students who trained in this particular group went back to good positions, postdoc positions in groups, international groups abroad, and almost most of them are in faculty positions in current Indian institutions, and they really will take the gravity wave research forward. At that particular time, when the first generation detectors reached their design sensitivity, a few of us really realized that it was really an important epoch, and we should really start participating in a gravity wave experiment. And this discussion started as early as 2007 during the ICGC meeting, where one of the young leaders of gravitational wave research, Rana Adhikari, suggested that we should have a gravity wave detector in India, and it was called Indigo. And then at the same time, we started collaboration with the Australians, who were also trying to build a detector by themselves. And a very important watershed event was the formation of the Indigo consortium in 2009 during the 20th anniversary celebrations at IUCAA, because this consortium basically brought together not only the data analysis and source communities, but it also realized that if you really want to have a detector or a gravity wave experiment in India, you really have to have a national consortium. You really have to look at the subsystem expertise which exist in different labs and bring them together. Bringing coherently under one umbrella this group of people is really what led eventually to first to LIGO Australia, and it allowed us to interact with the gravitational wave international community, the LIGO group, the group in Australia, and this finally led to the LIGO-India, as I will indicate. Normally, a few months back when we used to give talks on when do we think we can say something, we basically would say that when the detectors will start on, detections would be possible, but detections are likely to happen only a few years later. But we know that the story is different. Detections have happened, and the question is how often and what else? That's really the questions we have to answer over the next few years. And therefore, if you really ask, the detection of gravitational waves was the first mandate of the laser interferometers. It has happened. But the promise and real excitement is because it is going to be a new observational window to the dark universe, which will become eventually a tool for astrophysics and cosmology, and then eventually become an experimental probe for basic physics itself. And this is basically because of fundamental reasons related to gravity. Gravity wave signals propagate unattenuated. The observations are privy to aspects which are not accessible to electromagnetic astronomy, and therefore they have the ability to uncover new aspects of physics. The direct detection probes strong field regime of gravitation, and the important point is gravitational waves must occur in any relativistic theory of gravity, but the properties of gravitational waves in different theories can be different, and that is what we hope to be able to test eventually. So for example, once we start having routine observations, we think that it will be the dawn of multi-messenger astronomy, which will include a gravitational wave window. For example, if you have gravity wave observations coincident with short gamma ray bursts, it will test the connection between these two kinds of astronomy, and it will tell us what the progenitor should be. Again, you can put limits on the speed of the gravitational waves, etc., etc. Eventually, we will be able to do cosmology by using these sources of gravitational waves. But the important point is that if you really want to do multi-messenger astronomy, you really need localization of the gravity wave sources on angular scales with a latency of a few minutes. And therefore, how do you do localization of sources? It's exactly as the police do localization of cell phone by using TV towers. If you really had a number of detectors, you basically do triangulation. You measure time delays from different sites, and the timing accuracy determines the sky localization. So if you had two sites and one time delay, the source could be anywhere on an annulus in the sky. So as you add more sites, you would find that you would have more time delays, and therefore you can localize it. But when you look at the localization, when you do a system of simulations, you basically realize that if you had put the two detectors in the same beam tube, use the detector in Livingston and the Virgo detector, there are parts in the sky where the localization is not very good. But just move one of those detectors far away, for example to India, and immediately all these long ellipses become much more manageable, and the map is not very different if you put a detector in Australia, which is the furthest you can put it away. And if you have a detector in Japan, for example, you can do even sort of better. So the important point is that the source localization requires this global network, as Gwick had anticipated, and that is why the LIGO-India project really came into being. In addition to the advantages when you have a detector, an additional detector, The important point is the improved source localization required for multi-messenger astronomy. Simulations show that if you include LIGO-India, it improves angular resolution on an average by 4 times, and in some directions by a factor of 10 or 20. So, as I told you, because of the Indigo consortium, in 2011, preliminary discussions started for relocating the advanced Hanford detector in India. October 2011, a formal offer was made, and just in a month's time, a proposal had to be submitted because the Planning Commission was making its final decisions. So it was submitted to the DAE and the DST, presented at a meeting on mega projects. And I want to sort of tell you that even during this particular time, the project has undergone very rigorous reviews. We had 4 LIGO lab visits to Indian institutions. We went through 3 NSF reviews in these months. And in April 2012, which was a kind of deadline which we had from the US side, LIGO-India was included in the Atomic Energy Committee Commission meeting as one of the DAE mega projects. Again, in August 2012, at the highest level, the National Science Board basically had to make a decision. Do they install the 2 detectors in the same beam tube, or they change the scope of the project? It was a major decision, and they agreed to project change in scope so that eventually the detector could be located in India once the approval happens. So what is the LIGO-India project? The project is for the construction and operation of the advanced LIGO detector in India in collaboration with the LIGO lab, set up the Indian node of this 3-node network by 2022 and operate it for about 10 years. The important point is all the hardware components for the advanced LIGO detector along with the designs would be provided by the LIGO USA and its international partners, but the entire infrastructure, which is also a very big challenge, which costs about 1,200 crores over 15 years, had to come from the Indian side. If you are interested in the details of the LIGO-India project, you can find a link on it on our Indigo website. So the LIGO-India project really at this particular point involves on the USA side the LIGO laboratories at Caltech and MIT, and on the India side the 3 lead institutions are IUCAA, IPR and RRCAT. And the point is the project is in collaboration with the LIGO lab, and there are a lot of things related to the training, etc., which will happen, which will come from their sides. The project is a very complex project, so we had to decide who would do what. So for example, IUCAA is responsible for site selection and survey, data analysis and computing, creating the science and the HRD. IPR for building the infrastructure, the vacuum, and implementing part of the control data system. And for the optics and the detector, the RRCAT. And the basic point which was decided by DAE is that the activities would be under an MOU among the lead institutes, and the scientific participation in the LIGO scientific collaboration is by the Indigo LIGO scientific collaboration, which is managed by IUCAA and Indigo under an MOU. Now, I will sort of go to the fact that there are groups at these lead institutes, which really work on LIGO-India aspects. And as I said, the important point, the first thing which we really need to do is worry about sites. Are there suitable sites in India? With assistance from IUCAA and looking at some support from ISER Calcutta, we basically have been able to have seismic surveys of some selected sites, and basically it turns out that there are some good sites which are even better than the USA sites. When you do, the Deccan Plateau is seismically very, very stable. And then, even though we don't have a project, over the last few years, we have looked at many sites, shortlisted them, done engineering studies of them, shared that information with the LIGO people. There is a technical report which already has been put together by IUCAA. So in terms of identifying a site, a lot of homework has been done, but remember, since it's not a formal project, there is so far we can go and not beyond. There is also work on the follow-up, because IUCAA has other branches of astronomy, so work towards setting up the follow-up is also happening at IUCAA. There is a data center at IUCAA, and recently, as you know, there is a ICTS cluster also. So again, the data analysis infrastructure is there at both these institutions. RRCAT, which is planning to set up the optics, plans to set up a laboratory off-site, that the engineering drawings for that are there. And then work related to understanding the optics in terms of suspensions and so on. A lot of work has been done over the last couple of years in collaboration again with the GEO group, which is in charge of the lasers. Again, there is a group of about 7 people who's working on it. So what I really want to show is that even though it's not an approved project, there are teams at the 3 lead institutions doing whatever can be done to come up to speed. I'll sort of skip these sort of details. These are small things, things which are done in the lab. And finally, as I told you, IPR has to basically convert all the drawings for the vacuum infrastructure and the civil infrastructure. Remember, the LIGO, we have to make a clone of the LIGO detector. The units in US are strange. We have to convert it to metric. All the drawings have to be converted. So there is a very large work involved in that, and that has been done at IPR, and they are ready again with this. These drawings are being validated by the LIGO team and by the RRCAT team. Again, a dedicated team working on these particular aspects. So what is Indigo? Indigo really is a multi-institutional, multidisciplinary consortium. It has 3 principal lead institutions, 9 other nodal institutions which involve educational institutions like IITs and ICERs. And in addition, individual scientists also are members of this particular consortium. Starting from a bunch of theorists and data analysis people with a very limited number of experimenters, what we have really achieved is a steady growth of people who are interested in this particular project. This is I think, one of the important things which has happened. A subset of this already works with the LIGO scientific collaboration. Again, participation in LIGO scientific collaboration by my distinguished colleague at IUCAA, Sanjeev Durandar, was just a small kind of team. So when we began, we had a very small team here. But today, we are happy that we are about 61 people. And the important point is we have a healthy mix of experimenters. So basically, what do we dream? 2022, there will be a global network of detectors, including one in LIGO-India. And the important point is, if you look at the thing here, what is shown here is that there are different, how many systems do you detect, but how many are localized in a region of about 5 square degrees. You can see that until LIGO-India comes online, the number does not get to significant numbers that we can do gravitational wave astronomy. So the message is, as the global gravity wave network expands to include LIGO-India, the successful operation of advanced detectors will transform the field from gravity wave detection to gravity wave astronomy. So what is the current status? Final decision is by the cabinet is still sort of. I am a theoretician. I spent all my life doing gravity wave source modeling, but that's not what excites me. What really excites me is this following statement from the NSF, Beverly Berger, who said, this experiment involves technology, and every single technology they are touching, they are pushing, and there's a lot of different technologies they are touching. It is this which, even though I'm a theoretician, excites me more, basically because if you look at this particular project, its interface, of course, begins with fundamental physics, but then there is a very important thing related to precision measurements. Then, of course, interfaces with technologies, and every one of these technologies at the cutting edge, at the frontier. Remember, you cannot go beyond the technology required, at least on the Earth at this particular point, in all these particular areas if you want to detect gravitational waves. So that's the important point. The other thing, of course, encouraging. What is the point in having ICERs? We don't have challenges for the students. So you have great, great kind of money being put in starting in these higher institutions. But unless you challenge the young, I think you are not doing enough. So I think what we really think is that the subject also can capture the imagination and therefore add to other things which you do. It is these interfaces which excites all of us, and it is what really helped us really sort of to say that, yes, we should go ahead and do this. So the point is that you have, as Sanjeev mentioned, that Galileo's telescope has launched optical astronomy, but we think that the major revolution in astronomy is around the corner, and the important point is India has the opportunity to play a key role because, as I mentioned, LIGO-India will be a critical element in this global network. The important point is that most of the universe is electromagnetically dark, but we can reconstruct it better once we start hearing the footfalls of Einstein's messengers, which will be heard in the gravity wave detectors in the near future, especially when LIGO-India joins the global network. As Ajith mentioned, Einstein seems to be right, but we are not satisfied. We want to ask, is he 100% right? And that is really the whole point, because we know that many enigmatic aspects of gravity still remain. So though we begin from astronomy, decoding gravitation is the holy grail, and this odyssey encompasses the whole universe. Most of it is dark, but there is a symphony in gravitational waves which is happening from these chirps and wails of dying stars and black holes, and maybe, as Spenta says, the murmurs of the Big Bang. So I'll just end with my point. Change is possible only if you dare to dream, are not afraid to fail, and have the humility to collaborate. The gravitational wave community was built on these ideals, and I hope Indigo will emulate it and go beyond it to get there in time. Thank you for your attention.
Thank you, Professor Bala Iyer, for that very wonderful and inspiring talk. We have time for a few questions, and then Rajesh Gopakumar would like to make an announcement, but let's take some questions first. Tarun.
This is not a question, but a comment. Bala mentioned that LIGO-India will be transformational. So one of the in the public release from Indigo press conference, you would find an analysis we did. You see this huge error ellipse in location, which is about 600 square degrees. And we asked the question, if such a source came up when LIGO-India was there at a location in India, what the error ellipse would be looking like. I have the picture in my laptop, but I can't power mount my laptop yet. But it's a tiny dot. So 600 square degrees, and this is, our estimate is 5 square degrees. Okay, so for this particular source, it would have made a factor of 100 difference in the angular location. Okay, so that's like, 3,000 moons versus some 30 moons on the sky.
I see. That's very impressive. Any other questions or comments? Rohini, yeah. Please.
Appreciating the comment made by Bala here last, that you have the humility to collaborate. I think one of the things that hits one when one thinks of being a particle physicist, I can't avoid saying it, the two most important discoveries of the last 5 years, one being the Higgs and the second being what we are discussing today. And both of these would not have been possible unless we had these really mammoth collaborations. And I think one of the things that we, not just science, we need to scientists also need to understand that some of the questions and the most fundamental questions need big, massive, collaborative efforts, and somehow one should not underrate them ever.
Thank you.
That's true. Okay. I thought I saw one hand.
Baji.
Oh, Baji.
You can go back to that plot of localization ellipses for different locations of. You mentioned that if you had a detector in Japan, the ellipses seem to be sharper than what would it be if you had one in India. How could that be? Because the baseline between LIGO and Japan would be much less than...
No, there were 5 detectors.
Oh.
It is not a 4 detector network, but a 5 detector network. The picture which I showed you was a 5 detector network. I didn't show it only with Japan.
Oh, I see.
Yeah.
Okay.
You mean that was with LIGO-India and Japan?
Yeah, it's a 5, yeah. Just to show that when you add detectors, you do even better.
Okay, we're kind of running out of time, so maybe let's thank Bala again for a very nice talk. And
Thank you, all of you, for the wonderful talks, all the speakers of the session, and to Sandeep for chairing it. I just have a couple of small announcements.